So let's pick up and talk about the endocrine system. We left off with the hypothalamus and the pituitary gland, and we're going to continue that discussion. We need to finish up our pituitary gland. Just to re-emphasize this, the pituitary gland is the master gland. It releases and synthesizes the most hormones of any gland in the endocrine system. About half of what we're going to cover is going to be related just to the pituitary gland. So as we look at our pituitary gland, it's going to be regulated several different ways. It's going to be regulated by the hypothalamus. Most of the pituitary regulation will come from the hypothalamus, but our pituitary gland can also respond to stimuli from other parts of the body, whether these stimuli are hormonal, neuronal, or just a chemoreceptor where the pituitary gland is measuring a chemical directly in the bloodstream. Now, when we think of being stressed out, I don't know, maybe you have a big lab exam or a lecture exam, whatever it is that stresses you out, there's a hormone that's probably going to be released into your body, and that hormone is called ACTH, adrenal corticotropic hormone. And this hormone is going to come and be released. It causes you to be stressed out and has the corticoids, the adrenal glands, to be activated, and we'll have adrenaline released from the adrenal glands. Another method of control for our pituitary gland is going to be from the hypothalamus, triggering prolactin secretion. Prolactin, as we talked about last class period, is a milk that promotes lactation or causes an individual to produce milk from their mammary glands. And just to reemphasize it, producing milk is not the same thing as releasing milk. To release the milk, we need to use oxytocin to cause those smooth muscle contractions of the mammary gland. Now, when we look at the posterior pituitary gland, it's going to be controlled directly by the hypothalamus through neuronal interface. When we look at the anterior pituitary gland, there's a portal system or some blood vessels that carry hormones from the hypothalamus to the anterior pituitary. With the posterior pituitary, we don't have the bloodstream delivering hormones from the hypothalamus. Instead, we have neurons delivering action potentials and delivering hormones that have been synthesized and need to be stored. Classic things that cause the response of the hypothalamus to trigger the release of these hormones include suckling on the breast. That stimulation of the breast is going to trigger the posterior pituitary to release oxytocin. So when the breast is suckled, there will be smooth muscle contractions that will cause milk letdown. Another hypothalamic response is going to be some osmoreceptors. An osmoreceptor is a word we haven't talked about yet. So let's pause for a moment. Osmoreceptor. An osmoreceptor is a special neuron that measures the osmolarity of the bloodstream. It's a fancy way of saying it measures the water content. When osmolarity is going up, the water content is going down. So as our hypothalamus is measuring the osmolarity, or the water content of the bloodstream, it's going to control the release of antidiuretic hormone. If the water content is going down, osmolarity goes up, and the hypothalamus will trigger the posterior pituitary gland to release antidiuretic hormone. This is a classic negative feedback loop. So when we're dehydrated, we release the ADH and retain water to minimize the effects of that dehydration. Another example is going to be the hypothalamus and the pituitary and the thyroid gland. Here's another negative feedback example. So when we look at thyroid stimulating hormone, thyroid stimulating hormone is one of the 6 hormones of the anterior pituitary I asked you to memorize. And that thyroid stimulating hormone, or TSH, is going to be released in response to thyroid releasing hormone. So if we're in a situation where we need to have more T3, T4, more thyroid hormones, the hypothalamus will detect that and release TRH that goes to the anterior pituitary gland. when thyroid-releasing hormone goes to the anterior pituitary gland, it causes the anterior pituitary gland to release thyroid-secreting hormone, or stimulating hormone. Thyroid-stimulating hormone will then go to the thyroid gland, and the thyroid gland, in response to TSH, will release T3, T4, the thyroid hormones. And those thyroid hormones will go to the target organs, which are numerous throughout the body. Now, if there's a low concentration of thyroid hormones, we don't have this inhibitory effect on the hypothalamus and the anterior pituitary gland. But as more and more T3 and T4, more and more of these hot thyroid hormones are being released into the bloodstream, they'll travel to all tissues affected by the bloodstream, which is every tissue in the body. They'll go to the hypothalamus, they'll go to the posterior pituitary gland, and when thyroid hormones, the T3 and T4, get to the anterior pituitary, they inhibit the secretion of TSH. When these thyroid hormones get to the hypothalamus, they inhibit the secretion of thyroid-releasing hormone. So in this way, thyroid hormones, T3 and T4, will prevent their own synthesis. It's a negative feedback loop. As you have more and more of this chemical in your body, that chemical will prevent more of itself from being produced. Let's talk about giving birth. This is a classic positive feedback loop. There's not many positive feedback loops in the body. Giving birth and oxytocin and uterine contractions is kind of overplayed, but it's easier to understand, which is why it's the classic positive feedback loop. So let's think of a woman in the third trimester of pregnancy. Typically about halfway through the third trimester of the pregnancy, the baby will descend. And what typically is going to be associated with that, all of a sudden lung capacity increases, and you're like, oh, I can breathe again, and something else will happen as the baby descends. As the baby is descending, the baby is going to cause the inferior margin, or the inferior end of the uterus to start stretching out. And as that baby causes the bottom, or the inferior end of the uterus, to begin to stretch, that slight, gentle stretching of the uterus is going to trigger the release of oxytocin from the posterior pituitary gland. And oxytocin causes smooth muscle contractions. Our uterus, or for the females in here, the uterus is made of smooth muscles. So in response to oxytocin, the uterus starts to contract. And as the uterus contracts, the child gets pushed farther and farther down through the cervix and into the birth canal, which causes more stretching, which causes the release of more oxytocin, which causes more contractions, more stretching, more oxytocin, more contractions, more stretching. It just builds and builds and builds and builds. It's a positive feedback loop. And what we typically find is that pre-labor or early labor, when there's very little stretching and very low levels of oxytocin, can go for hours. For my wife in particular, she had 24 hours of pre-labor, where she was having a for child number one, I should say. So about every 10 minutes, she'd have a uterine contraction. And I remember very specifically, first kid, I was freaking out. I'm like, oh my gosh, what do I do? So I was gonna call in sick to work that day, and she's like, no, this is dumb. She says, she sent me to work that day. She went to work, worked an 8-hour shift, well in labor, and then we got home that night, and then things started to progress a little bit faster. And then Tim was born. So as the cervix, or excuse me, as the uterus is stretched and stretched and stretched, there's more and more oxytocin. We need something to break the cycle of stretching the uterus and releasing more oxytocin and more contractions and more stretching. To break the cycle, the woman will give birth. And once the woman gives birth, the uterus can contract in on itself, and there's less stretching and less oxytocin, and the positive feedback loop will be broken. Let's talk about growth hormones, sometimes referred to as HGH, or human growth hormone. Growth hormone is the most widespread hormone in the body, in that it affects the widest variety of tissues in our body. In particular, it has a profound effect on cartilage, bone, muscle, and adipose tissue, or fat tissue. Our human growth hormone is going to travel to the liver And while that growth hormone is in the liver, it will stimulate the liver to produce some growth stimulating factors. And these growth stimulating factors are then going to go from the liver to travel to other parts of the body to cause these tissues to go through cellular division, mitosis and cytokinesis. Now, here's a new term that we need to camp on for a little bit here. Hormonal half-life. This is a key term, particularly if you take any kind of pharmacology classes, nursing majors. I believe this is covered in your pharmacology classes, or at least every pharmacology curriculum I've looked at has covered half-lives. We have hormonal half-lives, or we can have drug half-lives. Think back to your chemistry prerequisite you took before you came to this class. It's the same kind of math associated with the half-life of a radioactive isotope. How much time needs to go by for half of your favorite chemical to be removed from the body? And some hormones have longer half-lives than other hormones. Generally speaking, the longer the half-life, the more persistent the hormone's going to be, and the higher the effects of that hormone. As a rule of thumb, when we're thinking of hormonal half-lives, the lipid-based hormones that are not water-soluble and cannot be urinated out will have longer half-lives than the protein-based water-soluble hormones. So that's just a general rule of thumb. Yes, there are individual exceptions, but as a guiding principle, if it's water-soluble, it will have a shorter half-life. If it's water-insoluble or hydrophobic, it will have a longer half-life. It takes a longer time to remove it from the bloodstream. Now, when we look at growth hormone has a half-life of about 6 to 20 minutes. So that growth hormone that's released from the anterior pituitary gland only has a very short period of time to travel to the liver and stimulate the production of IGF-1. And once IGF-1, that growth factor, number 1, is produced, that growth factor has a half-life of about 20 hours. So as we're looking at these two hormones, that growth hormone dissipates very quickly from the bloodstream, and then IGF-1 lingers for a much longer period of time within our bloodstreams. Now, our liver, is that jack of all trades, master of none. Question? To my knowledge, it's not human growth hormone, but it's human chorionic gonadotropin releasing hormone. Are you talking about pregnancy tests? Yeah, to my knowledge, it's not growth hormone. We'll talk about that hormone, though, in Bio 314. And actually, on the note of pregnancy tests, the dollar store pregnancy tests are just as effective as that $15 pregnancy test from Walmart. Exact same manufacturing. There was a really cool lab I did in grad school where we took chorionic gonadotropin releasing hormone and exposed the same concentrations to different pregnancy test kits. And the cheapy one worked just as well as the expensive one. Food for thought. So let's talk about the liver. As we're looking at the liver, it's that jack of all trades, master of none. It's really hard to categorize what body system to put the liver in. So our liver is going to increase the rate of protein synthesis. It's going to boost the rate of transcription, translation. Yes, we're going to come back to those terms from Unit 1. Transcription is copying DNA to messenger RNA. Translation is taking the messenger RNA and converting that information to a polypeptide or a protein. And our liver is also, in response to growth hormone, going to suppress protein catabolism. Catabolism is a term I did not talk about when we covered chapter 24. A catabolic chemical reaction takes a big chemical and breaks it down into smaller pieces. So if we suppress protein catabolism, we are suppressing the digestion of protein molecules in our body, intracellular protein digestion. We're also going to find that in response to growth hormone that we're going to have an increase in lipid metabolism. In other terms, we're going to digest our fats. We're going to take the fat That triglyceride, chop it up into a glycerol and fatty acids and utilize the fat for energy or ATP production. Our growth hormone will also stimulate the liver to have some carbohydrate metabolism. In particular, it's going to take the glycogen stored in our liver, and it's going to take that glycogen and turn it into glucose. It's also going to take those fatty acids from the lipid catabolism and turn those fatty acids into glucose and or ATP. The key thing I need to emphasize here is that the purpose of this carbohydrate metabolism effect of the liver is that we need carbs for our brain. Our brain functions really well with carbs. It's designed to utilize carbohydrates for ATP generation. Other tissues of our body can utilize proteins or fatty acids. Our brain does not do a good job of utilizing these alternative fuel sources, but our brain needs the carbohydrates. So make sure you get a meal before a big test because you need to have some brain food or some blood sugar. We also find that growth hormone is going to promote the release of some minerals into the bloodstream. We're going to retain sodium, potassium, and chlorine and calcium ions. These ions that are responsible for regulating action potentials within the body. And we need those ions so that we can have more regulation of the growing tissues in addition to a myriad of other things within our bodies. Now, let's talk about how to hack your body. I know it's kind of cliche. You know, I'm a college student, I need to pull an all-nighter, I don't have time to sleep, I'm too busy to sleep. That's nonsense. You are never too busy to get a good night's rest. You are going to shortchange yourself and have a dramatic decline in health, a dramatic decline in mental performance. Everything will suffer if you don't get a good night's sleep. So for me personally, I have to schedule my sleep. I have an alarm that goes off that says, oh, it's time to start bedtime for the kids so that I can get to bed at a reasonable time because I have to get up pretty early to get here. So when we think of sleep and how it affects growth hormone and tissue repairs in our bodies, we need to have sleep because those first 2 hours of sleep are going to secrete lots of growth hormones into our bodies. And think of this in terms of a tissue repair perspective. Student athletes, when you go through your workouts, you have lots of tearing of the myofibrils within your muscle fibers. You need to repair that damage that occurs. If you go and have a good workout and then don't follow that good workout with a good night's rest, you're not going to have the gains you were hoping for. This is when you repair the damage that you incur in your body. We also find that growth hormone is going to be released by a hormone known as ghrelin. Ghrelin is a hormone that we'll talk about more when we get to the digestive system. It helps to regulate hunger. When we have a stomach that's contracted and not stretched out, the stomach will release the hormone ghrelin, and ghrelin is known for causing individuals to feel hungry. Now, as we age, we have less and less growth hormone in our bodies. In other words, as we age, our ability to repair little bits of damage we incur throughout the day declines. Growth hormone is a key hormone that helps us repair the damage to our cartilage, our skeletal muscle tissue, our bones, and to minimize fat gains. So when we look at someone who's young and healthy, they'll have about 6 nanograms per milliliter of growth hormone within the bloodstream. As someone who's aged or in the geriatric end of the spectrum, they'll typically have 1.5 nanograms per milliliter. So in other words, right now, you're at the peak, you're at the prime, your ability to recover from damage, recover from injuries is the highest that it's going to be for the rest of your lives. We typically hear that cliche, young people recover quicker than old people. One of the reasons why young people recover from injuries quicker is because they have a much higher concentration of this growth hormone that allows them to repair their tissues. Let's see if I can make this bar go away on the bottom. There we go. So as we are aging in our bodies, the composition of our body is going to change. And no, I can't make it go away from the bottom. So let's talk about the general trend, because I can't see the numbers right now. when you're younger and healthy, you have less fat, more bone, and more muscle. But as you age, your bone density decreases, your muscle mass decreases, and your body composition shifts from bone and muscle to having increasing proportions of adipose tissue as you age. And if we think of growth hormone stimulating the breakdown of lipids, if you don't have as much growth hormone stimulating the breakdown of the lipids, you'll have a buildup of lipids. If you don't have as much growth hormone stimulating the regeneration of your proteins, you'll have less protein-dense skeletal muscles. So it makes sense if you can connect it to what growth hormone does to our bodies. All right, we're done with the pituitary gland. Let's move on. That wasn't a dramatic pause. I had a brain hiccup. That's why I paused. So let's talk about the other glands of the body. These glands are not as involved as the pituitary gland. It's going to be much snappier as we move through the rest of the endocrine system. Let's talk about the pineal gland. Another name for the pineal gland is the epithalamus. So write that on your margins if it's not on the slide. The pineal gland, also known as the epithalamus, is the gland that is not necessarily above. In my opinion, it should be called the posterior thalamus as opposed to the epithalamus, but the technical name is epithalamus. Our pineal gland is at the posterior of our brainstem. And as we look at that epithalamus, the hormone I want you to connect to the epithalamus or the pineal gland is melatonin. Now, this epithalamus is pretty large when we're younger. And then as we age, it starts to get smaller and smaller and smaller. And let's think of some changes that occur. First, I need to just mention before I get to the next slide, melatonin helps us to sleep. So when we think of melatonin, this is going to regulate our circadian rhythms. It's going to regulate our sleep-wake cycles. And what we typically find is that young kids, they have a really big fat pineal gland. And the tendency for young children is that when it's dark outside, they typically fall asleep. Well, not infants. I should say like preteens or like tweens, like grade school age kids. I would really wish my infants would have slept last night. So these little kids, that are in elementary school, when it's dark outside, they sleep. When it's awake outside or light outside, they're awake. You probably remember during summer vacation, Mom, it's light outside. I don't want to go to bed. Little kids have a really hard time falling asleep when it's daylight out. And part of the reason for this is the pineal gland is abnormally large compared to the rest of their brain. And then puberty hits, and you became a teenager. And all of a sudden, it's really easy to stay awake in the middle of the night. And the ability, like daylight and nighttime, all of a sudden don't really have an impact anymore on the sleep-wake cycles. And the cliche for teenagers is to stay up till 2 or 3 in the morning, and still kind of the cliche for your age bracket as well, or if you're Miss Launterich. I get emails from her sometimes at 2 or 3 a.m. in the morning. And I'm like, I'm waking up in like an hour or two. I'm not going to respond to that email. So let's talk some more about how to hack your bodies. When we think of growth hormone, you need to get sleep so you can maximize the effects of that growth hormone, the positive impacts of that growth hormone. So how can you get more sleep? The melatonin secretion from the pineal gland is going to be influenced by exposure to ultraviolet or blue shifted visible light. So when we look at the light bulbs in your house, the kinds of light bulbs in your house can influence your sleep-wake cycles. And I'll admit I remodeled my kitchen last summer, so I know more about light bulbs than most people because I spent a lot of time reading up on them. When you are trying to sleep, you want that warmer, that redder light, which is typically like when we look in this room, kind of like the fluorescent lights on the side of the walls, like kind of a red tinted or orange tinted light. That light doesn't have a lot of blue wavelengths in it and won't depress the secretion from the pineal gland. On the other end of the spectrum, if you want to be alive, awake, alert, enthusiastic, you want to have and I did sing that all the time at Boy Scout camp. You want to have a lot of blue shifted or cool light. Apparently my ability to annotate right now is going away. All right, it's gone. Let's try one more time. All right, it's gone. All right, I have no idea why that happened. So you want that blue shifted light. So when you're thinking of like what kind of light bulbs to buy for your house when you get to that stage of life, you want the blue tinted light for like the office, the kitchen, the bathroom. You want the yellow tinted light for the bedroom, the living room, the den, the areas where you're kind of relaxing and cooling down and settling down. People that don't have that good exposure to bright blue shifted light, particularly in winter, are going to develop something known, oftentimes will develop something known as seasonally affected depression or SAD. A good way to combat that is to have really bright blue tinted lights that you could expose yourself to, or you could buy a happy light, which are really pricey. It's about $150 for a little light box. A more recent phenomenon is smartphone insomnia. Your smart devices are hurting you in addition to helping you. Yes, it's super convenient. Yes, there's so many wonderful things associated with having, everything in your pocket in one device. But I can't emphasize this enough. The blue tinted light from that smartphone contributes to insomnia. One of the worst things you can do is binge on Netflix on a smartphone right before you try to go to bed at night, because all that blue tinted light is going to make it much more difficult for you to fall asleep. It will inhibit melatonin production by the pineal gland. So there are some options out there. I know Amazon Fire and iOS have built into their operating systems a blue light or nighttime filter that helps a little bit. So if you absolutely want to watch whatever it is you want to watch, turn on the blue light filter. Everything gets shifted to the red end of the spectrum. But even better, just don't use the smart device for an hour or two before you're trying to go to sleep, so you can upregulate that melatonin production and have better sleep. Next gland, let's talk about the thymus. When we think of the thymus, I want you to think immune system development. More than anything else, I want you to associate the thymus with the development of the immune system. Our thymus changes significantly as we age. When we're brand spanking new, when we're still wet behind the ears, we have a really large thymus when we're newborns. And the reason why we have a really large thymus relative to the heart, so maybe I can annotate on this screen. Oh, I can magically draw on this screen again. So as we look at an infant's thymus, the thymus of an infant is the size of the infant's heart. So relative to the body size, it's ginormous. Why would an infant need to have a ginormous thymus? Infants don't have any immunity yet. They have the passive immunity from their mother's breast milk, and that's it. They haven't developed any of their own T lymphocytes. So when we think of the thymus, an infant needs a really disproportionately large thymus because they're working overtime to develop lots and lots and lots of T cells to aid with their active immune system or acquired immunities. As we age, our thymus becomes smaller and smaller, and our ability to produce new T cells or new T lymphocytes is diminished accordingly. So let's think of this in terms of practical, just real life applications. When there's a flu outbreak, or unfortunately we have measles and whooping cough outbreaks again now, which just disgusts me, especially in a developed country like America. When there's these outbreaks, one of the reasons why they typically will say young children and aged or geriatric individuals are at risk has to do with the thymus. The young children haven't been around long enough to develop the immunities or the partial immunities, and then the geriatric population has a thymus that's a little tiny shriveled up mass of connective tissue, and they don't have the ability to easily develop new immunities. So that's why those two populations are at risk when there's an outbreak. It's all related to the thymus, but because of two different reasons related to the thymus. One hasn't been around long enough for the thymus to do its job, and the other population has effectively a non-functional thymus. Now, as we look at the thymus, there's multiple hormones that are released from the thymus. We have thymopoietin, thymosin, and thymulin. Thymosin, of those hormones, is the most potent in terms of T cell maturation and development. So that was the thymus. Let's move on to the thyroid gland. Our thyroid gland is going to be superior to the thymus. So the thymus will be right in between the lungs. Actually, well, I'm still talking about the thymus. Let's be on the thymus slide. The thymus is right in between the lungs. Typically, it's going to be posterior to the heart within the thoracic cavity. Or sometimes will be just a little bit superior to the heart, depending how we're aging. As we look at the thyroid gland is going to be associated with the larynx. So if you palpate your throat, you can feel your Adam's apple or your laryngeal prominence. And then if you squeeze just inferior into the sides of that, you can squeeze your thyroid gland. Our thyroid gland has two lobes with a little isthmus or a little band of tissues connecting the two lobes that are left and right to the trachea. And within our thyroid gland, we have thyroid follicles. These thyroid follicles are going to contain different kinds of cells that secrete different hormones. As we look at these cells of the follicles, we call them follicular cells of the thyroid follicles because they line the follicles, or the tiny tubes within the thyroid gland. Now, as we look at the thyroid gland, most individuals will just say collectively, the thyroid gland secretes thyroid hormone. And when someone says thyroid hormone, they mean a combination of two separate hormones, or a cocktail of two separate hormones. Those two separate hormones are T3 and T4. T3 and T4 are called T3 and T4 because of the number of iodine atoms in each of those hormones. T3 has 3 iodine atoms. T4 has 4 iodine atoms. The technical name for T3 is triiodothyronine, and then T4 is just referred to as thyroxine. I really wish it was referred to as tetraiodothyronine, but the name doesn't make that much sense, unfortunately. So thyroxine is the one that has 4 iodines, and then the one that has the tri prefix in front is the one that has the 3 iodines in it. Now, when we look at T3 and T4, these hormones have a lot of effects on the body. They're very widespread effects. Probably the most notable effect is T3 and T4 cause growth hormone secretion. And growth hormone affects nearly everything in the body. So if your thyroid hormone levels are kittywampus, your growth hormone levels will be kittywampus, and then you'll have widespread symptoms all over the place. I'm willing to bet that most of you know somebody who has hypothyroidism, a thyroid gland that's not producing enough thyroid hormone. And these individuals with hypothyroidism are going to have a decreased metabolic rate. They're going to have decreased heat production, decreased alertness, decreased growth hormones, decreased reflexes. Having hypothyroidism, or not enough T3 and T4, is a big deal. It causes a lot of health problems. So most individuals that have hypothyroidism are going to have rapid, massive weight gain in a very short period of time. We're talking about 100 pounds within 6 months. As we look at the cells associated with the follicles, the cells that are around or in between the follicles are called the parafollicular cells, also known as C cells, C for clear. I'm a much bigger fan of the C cell name because they are the clear cells from the histology perspective. And when we look at those cells of the thyroid gland, they secrete a completely different hormone called calcitonin. Calcitonin was one we talked about with the skeletal system. If you have too much calcium in your blood, calcitonin will lower the blood calcium concentrations. And as it lowers that concentration, or to lower the concentration, osteoblasts, the bone-building cells, will be upregulated and will have thicker and denser bones produced. So, let's pause for a moment. I've been monologuing long enough. Let's have a review question. Which of these hormones does not stimulate the release of another hormone by its target cells? I'm going to give you some more time. This is a tough question, particularly because there's a bunch of pituitary hormones on this one. Which of these anterior pituitary hormones does not stimulate the release of another hormone by a target cell? And I gave you an extra 30 seconds for this review question. Our options are thyroid stimulating hormone, growth hormone releasing hormone, adrenocorticotropic hormone, prolactin, and thyroid releasing hormone. All of these hormones but one are tropic. They cause the release of another hormone in the body. All right, let's take a look at our answers. Prolactin is the only hormone, PRL, prolactin was the only one that does not stimulate the release of another hormone in the body. Prolactin stimulates the production of milk by the mammary glands. If we look at TSH, thyroid stimulating hormone, comes from the hypothalamus and will cause the anterior pituitary to release, thyroid stimulating hormone comes from the anterior pituitary and causes thyroid hormone to be released. Growth hormone releasing hormone will cause the anterior pituitary to release growth hormone. ACTH, adrenocorticotropic hormone, is going to travel to the adrenal cortex and cause corticoids to be released. We haven't talked about the specific corticoids yet, but it causes corticoids to be released. And then thyroid releasing hormone comes from the hypothalamus, goes to the anterior pituitary, and causes the anterior pituitary to release thyroid stimulating hormone.
If that doesn't stimulate something else, then how come oxytocin and that doesn't stimulate?
So I'll repeat that question. If prolactin doesn't stimulate the release of another hormone, how come oxytocin and prolactin have such a similar function? Oh, oxytocin and prolactin are oftentimes going to be interrelated with each other. So if a woman is pregnant, not only does she have increasing concentrations of prolactin in her body, she's also going to have slightly increasing concentrations of oxytocin in her body as well, particularly right at the end during labor and delivery. But they have separate control mechanisms from each other. Otherwise, if we think of some of the effects of oxytocin and how it's being produced, if oxytocin triggered the production of milk, then having an orgasm would also cause someone to start lactating. So we need to keep these functions separate from each other. And particularly for the males, that would be awkward. So, we also have parathyroid glands. And there's some interesting historical context of the parathyroid glands. As we look at our parathyroid glands, and how we're doing at time, we have about 9 minutes left. Our parathyroid glands are one of the more recently discovered endocrine glands within the human body. We've still known about them for a long time, but before we knew about the parathyroid glands, which are 4 little nodules that are on the posterior of the thyroid. When a patient would have a thyroidectomy, the surgeon, who didn't know about the parathyroid glands, would just cut everything out, including the parathyroid glands. And when these individuals lost their parathyroid glands, they would generally die within a couple days because of a very important hormone released from the parathyroid gland. The parathyroids release, and I love this name, it's a very intuitive name. They will release the parathyroid hormone. What does parathyroid hormone do? It increases blood calcium concentrations. We already talked about this hormone in the skeletal system for our Unit 2 exam. And why do we need calcium in our bloodstream? We use calcium to contract our muscles. We use calcium to release neurotransmitters so we can have electrical activity in our brains. So when a patient had their parathyroid glands removed, before we knew about parathyroid glands, all of a sudden the blood calcium levels would plummet, their ability to contract muscles would be decreased, their brain activity would decrease, and within a couple days, they would be no longer with us. To treat this, if somebody accidentally has an immune disorder with their parathyroid glands, they can take artificial supplements of parathyroid hormone to help maintain blood calcium concentrations. But it's kind of like a diabetic that has to constantly monitor their blood sugar and then adjust their their insulin medications as their blood sugar fluctuates. Individuals that don't have a parathyroid gland anymore have to constantly monitor blood calcium concentrations and adjust their medications based on the concentration. So here's some interesting histology. We have a thyroid gland. So here's just a regular thyroid gland. Here we can see a follicle within the thyroid gland, and then on the surface, indented into the thyroid gland, we have the parathyroid gland that has unique and distinct histology from the parathyroid or from the regular thyroids. So those regular thyroid glands will have those follicles. The parathyroid gland does not have those follicular cells or the clear cells, the C cells that we typically associate with the thyroid gland. It's distinctly different looking under a microscope. And the adrenal glands are kind of complicated. We have about 4 minutes left in class. I think this is let's see how we're doing right here. Do we have a review question coming up? This is a really good place to stop. So on Friday, we will finish up the endocrine system.